Alright, the last part of chapter 4.6 is being able to apply Simpsons Rule. Okay, so that's Theorem 4.19. It says let f be continuous on the interval a to b and let n be an even integer. Simpsons Rule for applying this is approximated here. Integral from a to b of f of x dx equals b minus a over 3n times f of x0 plus 4 of x of f of x1 plus 2 of f of x2 plus 4 of f of x3, and so on and so forth. So, very similar to the trapezoid rule, except just a few minor things. So, notice in front now, we have b minus a over 3 times n instead of b minus a over 2 times n. And then there's a different pattern for the coefficients here. Just like the trapezoid rule, the first and the last coefficient will be a 1, and the pattern for the rest of the remaining ones on the inside goes 4, 2, 4, 2, 4, 2, 4, 2. So alternating back and forth between 4 and 2 is the leading coefficients. So you'll kind of see how that goes as we go through an example. So it doesn't go, like 2, 4, 2 back down to 1. It alternates starting at 4 and going 4, 2, 4, 2, 4, 2 for all the internal coefficients, and then the first coefficient and the last coefficient is just 1. We will be evaluating all the different values of the function as we go through. So this is going to relate back to the trapezoid problem. We're going to do the same exact problem, 0 to pi of sine of x dx. It's more for simplicity about reevaluating where we're getting our evaluation points and things like that and plugging into the Simpsons rule. So same as example 1, 0 to pi of sine of x dx. We're going to do it for n equals 4 and n equals 8, just so we don't have to rework a bunch of stuff. I did rework it here in the notes for you to use, but for simplicity here, so delta x, if you need to review that, go back to the first video. We will be evaluating at the points 0, pi over 4, pi over 2, 3 pi over 4, and pi. So that still comes from b minus a over n, so pi over 4. Over here on the left I showed how we get those points. But the important part about this problem is being able to apply Simpsons rule. So we will do pi minus 0 divided by 3 times n, and that's 4 in this case. We're going to use pi over 12 out in front. Notice the pattern here. We're substituting into Simpsons rule, and we're going to evaluate each one of those points of the function. The function we're evaluating is sine of x. So we will start at 0 and end at pi, and then those 3 we had to calculate in between. So sine of 0 is 0, plus notice how this one has a coefficient of 4, so it's 4 times sine of pi over 4, so it's 4 times square root of 2 over 2, plus this coefficient is a 2. So it's going to go 4 to 4 on this one because of the number of terms we have. So the first and the last have a coefficient of 1, and then we go 4 to 4 for the coefficients with the remaining ones. So it's going to be 2 times sine of pi over 2, which gives us 2 times 1, which is 2. And then this term we're going to have 4 times sine of 3 pi over 4, which is 4 times square root of 2 over 2, plus 0. When we evaluate all these points, we get 2 square roots of 2 plus 2 square roots of 2. We're going to take all that and multiply it by pi over 12. When you do that, you get 2.0045, or if we go to only 3 decimal places, 2.05. Let's do the same thing for n equals 8. Now, you'll get to see the coefficients changing a lot better in this scenario. So we're going to still integrate from 0 to pi of sine of x dx. Now we're going to use n equals 8. So this is the same as the second part of the first example, b minus a over n. So we're going pi over 8. Over here on the left is how I showed how to get all those evaluation points. We walked through that step by step in the first problem. So notice our pattern for coefficients on Simpsons rule. The first coefficient is a 1, then we go 4, 2, 4, 2, 4, 2, 4, 1. That's the coefficients here. So I've written all that out. We have b minus a over 3 times n, so we're going to end up with pi over 24. And then we're going to have sine of 0. Then we're going to have 4 times sine of pi over 8 plus 2 times sine of pi over 4 plus 4 times sine of 3 pi over 8 plus 2 sine of pi over 2 plus 4 sine of 5 pi over 8 plus 2 sine of 3 pi over 4 plus 4 sine of 7 pi over 8 plus sine of pi. Alright, so I just read through all that. It was very exciting. But notice the first coefficient and the last coefficient are 1. Notice the coefficient on the function here goes 4, 2, 4, 2, 4, 2, 4. That's really like the most defining thing. So when we're doing Simpsons rule, we have to alternate those coefficients. When we did the trapezoid rule, all the middle coefficients were 2. So one of the big differences there. You're able to calculate all these numbers with your calculator. Make sure you're in radians mode. We end up with pi over 24 times 15.274, and we get 1.99. Now, if we kept more decimal places, so when you do this, maybe keep 6 decimal places instead of 3, you're going to get more accurate. So when I did this with 3 decimal places, I get 1.99. If you do it with about 6 decimal places, you'll get 2.003. So again, accuracy. The answer to this should hone us in and roughly be about 2 if we take a look at it. Okay, so there's using Simpsons rule, and we saw it you doing the trapezoid rule too, so we can see those two and compare. Let's do a Simpsons rule that's similar to your homework problem. Alright, and then this will be the last one in chapter 4 and in section 4.6, and then we'll be ready for our test soon. These are uploaded, and you should be able to go through all these notes as well on the website. So let's finish this up. We have example 4. We want to use Simpsons rule to approximate the integral 0 to 8 of the cube root of x, n is equal to 8. So, first step, finding delta x. Well, since we're integrating from 0 to 8 and n is 8, that makes it easy, alright? But we're going to do 8 minus 0 divided by 8, so 1. So our steps are 1. So we have to calculate the points we're going to start at. So we start at 0 plus 1. We're going to evaluate at 1. Then we go 1 plus 1, which is 2. 2 plus 1, which is 3. 3 plus 1, which is 4. So on and so forth. 7 plus 1, which is 8. So we have to end at 8. We have to start at 0. So we're going to evaluate 0, 1, 2, 3, 4, 5, 6, 7, and 8. Those are what we're going to substitute into this function here that's the cube root of x. And we're going to do it using Simpsons rule. So down here, alright, the leading factor is b minus a over 3 times n. So we're going to use 8 over 24, which reduces to 1/3. Okay, then we're going to substitute all these points here, and keeping track of the leading coefficients. Our coefficients should go 1, 4, 2, 4, 2, 4, 2, 4, 1. That should suffice for the number of values that we are going to evaluate here. So we're going to evaluate the cube root of 0 plus 4 times the cube root of 1 plus 2 times the cube root of 2 plus 4 times the cube root of 3 plus 2 times the cube root of 4 plus 4 times the cube root of 5 plus 2 times the cube root of 6 plus 4 times the cube root of 7 plus 1 times the cube root of 8. So paying attention, the first and the last term have a coefficient of 1, and then we alternate 4, 2, 4, 2, so on and so forth till we get to that last term, whatever it works out to be. Okay? Why are we using the cube root? Because that's the function. The function we're evaluating here at this integral is the cube root of x. So everywhere there's an x, we have to substitute in our values that we're evaluating. So when you guys do all this, you should be able to use your calculator, get these values. Again, try to keep a decent amount of decimal points here. I think I kept 4 or 5 decimal points throughout for anything that worked out at a decimal. When you add all these up and you get those numeric values, you should get something around 35.58949. Multiply that by a third, and you're going to approximately get 11.8632. So that really sums it up for chapter 4. We did the trapezoid rule, and we're doing Simpsons rule to evaluate areas under a curve. So basically, we're reviewing Simpsons rule in this section, making sure that you're keeping track of what the leading coefficients are and our evaluation points. It's really not too challenging. Just do a few for practice. Go ahead, just like normal. You have a question, go ahead and email me a question, and I will get back to you.